Why does everyone seem so excited about Effect right now? I was asking this question a few months ago as someone who's been using TypeScript since it first came out and JavaScript long before it. I know many of you are here because you like Elixir and I talk about Elixir, but most of us live in multiple ecosystems, and Effect makes TypeScript surprisingly palatable. While functional programming and effect systems aren't new, the recent rise in AI generated codebases makes libraries like Effect take center stage. We've all seen it: redundant helpers in every file, unbounded promise.all that exhausts system resources, tests that just test mocks, and the poor error handling you'd expect from a non corporeal author who will never be paged. Effect helps with all of this, but it has a steep learning curve and its docs are severely lacking. That's why I'm here to help. Today, we'll evolve a surprisingly complex set of functionality to develop an intuition around effect-oriented programming with the Effect TypeScript library. The project is simple at its surface. Check a list of URLs and determine if they return successfully. We will layer in concurrency, error handling, and dependency injection to show how an effect-based implementation can adapt to new product requirements without being a hassle. So stick around. This is Code and Stuff. As always, code is available with a link in the description. Let's get started. An effect is best described by way of example. Imagine we have this function to check the status of a page. The most obvious thing to note is that this function has many ways to fail. Fetch might throw for an invalid URL, bad networking, exhausted file descriptors, anything really. But the promise type only indicates the type of a successful outcome. Now, most implementations would end up adding a try-catch, something like this, but unless the return type becomes some custom object, it's going to be hard for a caller to know what might be rethrown. This could just as easily, instead of returning false, rethrow the error. I've seen this in a bunch of different code bases. Console.error inside of your catch, but then rethrow because you're going to need that error somewhere. The fact is, promise just isn't a good type. This function also contains side effects, making testing difficult. If we run the same function multiple times and it performs identically every time without any change to the outside world, it has no side effects. It's pure. Functions like fetch remove this pure predictability from the function. They make it hard to test and they can get us into trouble. It's easy to miss this, but the console.log and console.error statements are also side effects because they write to standard out and standard error respectively. But what if we embraced these behaviors and clearly indicated that the point of the function is to call the network and log out diagnostic information? What if our side effects were just effects? We'll come back to this idea in a moment, but it's the reason for the name of this library. But there's one more thing I don't like about this function. The moment it's called, it's running. Promises are eager. If it's called in a loop, you've immediately got n requests going out. Wouldn't it be nice to have a little more control over asynchronous functions? Maybe limit the number of in-flight requests to a number like 5, or interrupt a call. All of these things are possible, but they require modifications to the function itself. For example, you might end up adding the plimit library and then creating a limiter. This is an implementation of a semaphore in JavaScript. And then instead of directly calling your function, maybe you have to do something like this. Const result equals await request limit. This is going to take a callback. And we're going to wrap our implementation in this callback so that we can get a instance of this that is controlled and only executes once we enter this semaphore. Then we would return results. And this would have the effect of globally limiting the concurrency of checking to 5. I've also seen this inlined within some functions. There's some different variations, but we kind of had to change the semantics of the function in order to shim this in. Now, maybe you put this limiter inside of main and it doesn't go into check, but there's still this thing where you've got all of this concurrency that's happening, and because it's eager, you then have to go back and control it and limit it, restrict it somewhere. You still have all of those promises running, and so you don't get the efficiency that you might get through effect. So maybe you're cool with this, but I think a great function is one that stands alone and has a minimal surface area. One where its possible failures are clearly typed, and one that gives the caller the ability to control whether and when effects occur. Here's a similar function written as an effect. Just like before, we run the network request, contemplate errors, log the response, and return the outcome. Proper error types are a big part of effect programs, so we have one for a site being unreachable. Effect.log replaces console.log. It has the same intent, but it's an instruction. We'll see why that matters in a moment. But think for a second. What would you expect the result type of this function to be? Promise a Boolean? Well, in this case, it is an effect that has Boolean, site unreachable, and never. The first slot is the success type. The second is all possible errors. And the third describes the effect's dependencies, of which this function has none. But I'll address the elephant in the room. What's with all this function star, yield star nonsense? In case you haven't encountered them, generator functions are a special form that allow us to return or yield multiple values as an iterator. These functions get paused between yield statements and only run when something iterates through their results. They're lazy. For a more simple example, this is a counter generator function. Let's type this as a number. So it's going to iterate the numbers from 0 up to a target number inclusive and yield them. We can call this function to kind of get an instance of the generator in this count to 2 declaration. And then, as a caller on the outside, we can make this function actually run. So we do that by calling next on the iterator or putting it into an iterator loop. And once we do that, we can see that the value 0 was emitted and then everything paused. If we do it again, 0 and 1, and if we go through the entire list and exhaust it, then we'll get the indication that this function was actually done. It's yielded everything and now it has returned. Now back in our example, yield star is just a shortcut to yield the results of an iterator, like an array or another generator. And it turns out that effects are actually just functions that yield a series of instructions to a runtime. This indirection gives the library all of its utility, controlling concurrency, canceling, being aware of execution scopes, everything. So when we yield star try promise, we're telling effect that at this point in our function, we would very much like for it to run the specified promise in a try catch. This also passes an abort signal in case the promise we're wrapping knows how to support cancellation. Then we can run the whole thing in effect.runPromise. Right now I'm just awaiting check, but we can do await effect.runPromise. This will give us a runtime instance and then execute the effect. And now we can see in the results that we requested example.com and got a true back. You might be thinking this is just promises with extra steps, but check out what we can do without modifying the core check function. First off, we can run this more than once. Let's call check up here, and we'll just call this run. And let's run this more than once. Compare this to promises, which run one time once they're started eagerly and can't be resumed. They have to be reconstructed, usually in a callback. This is why every retry helper in TypeScript uses a callback. But since effects just describe instructions, rerunning them is easy. In fact, it's so easy that effect.retry was built for this purpose. Let's replace our run effect with one that pipes through a effect.retry with an exponential backoff, and this schedule is just an import from effect the library. So now, if an error is thrown by our effect, we will retry with an exponential backoff based on a 100 millisecond starting value. These can be composed to describe really complicated policies. For example, we could create a retry policy that has jitter and it has 4 retries and it will time out at 10 seconds. All of this is very possible and we can just pass it into effect.retry. Now, if you're not familiar with pipe, what it does is it takes the result of one function and then passes it in as the first parameter to a call to the next function, and so on and so on. In Elixir, we have a specific operator for this, And in JavaScript, it hasn't really made it through the TC39 yet, so it's not available, but maybe someday this will be built in natively, and we won't need to have a custom function called pipe that does the same thing. Now notice that all of this is just plumbing outside of an unchanged core check function. This kind of reusability and an adherence to a strong set of built-in utilities helps keep the slop at bay. Addressing bugs and adding resilience happens at the edges instead of in bloated functions that just keep on expanding indefinitely. Now, so far, all of this has been about one URL at a time. But we can recreate what we had with that p-limit semaphore from before. Let's see what concurrency looks like in effect. So we'll replace our main function with one that has a list of URLs that we're interested in. And then we'll do a map over those URLs, and we'll map them through our check function. The result of this is going to be an array of effects that return booleans and might throw a site unreachable and have no dependencies. Then our run effect is going to be the result of not promise.all, but effect.all. Now this operates very similar to promise.all, but with a few extra little gadgets inside. So we'll pass our checks array in there, and let's set our concurrency to 2. We're going to run up to 2 of these at a time. Now, even though our main function declares all of this behavior, nothing has occurred yet. And that's because we need to pass this into effect.runPromise, and then pass in our run effect. We're going to await this, and then console log the result. And in our results, we've got 4 log messages and then 4 booleans. Example.com returned successfully, but /1, 2, and 3 all 404'd in response because those pages don't exist on that server. Now, it wasn't an error, it wasn't something that was thrown, but it would represent a check failing. Now, notice the fiber portion of our log statements. 3, 2, 2, and 3. Fibers are like threads, and because we set our concurrency to 2, we will only have 2 of them working on our checking. Each fiber will run through an effect all the way to its completion, and then it'll pick up a new one whenever it is ready. So in this case, fiber 2 ran 2 of our requests, and fiber 3 ran the other 2. If I were to set my concurrency to 3, then we would have 2, 3, 4, and 2. And if I set it to 1, everything's running on fiber 0. There's no branching that's going on. It's just walking through these one by one. So rather than building concurrency limits directly into the check function, we just specify them at the time that they're combined. The result of this function is itself an effect that has an array of booleans as a success, or it might raise a site unreachable error. The default semantics of effect.all are very similar to those of promise.all. That is, when one of the entries fail, the result is that first encountered error. But unlike promises, effect.all will cancel all other effects to clean up after itself. If I were to add a bad URL into the mix, then this program would blow up. We would hit that site unreachable error in the effect, and then run promise is going to raise that error as the error of the promise. And we've got a site unreachable after running through our functions. We got a couple of requests, and then everything blew up. But what about that cancellation? Just for diagnostic purposes, I'm going to edit the check function, and instead of just running a fetch and passing the signal in, let's observe the result by adding an event listener and watching the abort signal come into our check promise. Now if I save the program and I scroll up to where it ran, I can see that fiber 2 got a 200, fiber 3 got a 404, and then there were 2 running. One of them was our bad URL, and the other one was example.com/2, which was canceled when the effect.all knew that everything was going to fail anyway, so we might as well clean up and go home. And if we don't want this cancellation behavior, we can change the mode of effect.all. In promise.all, you'd probably switch over to promise.all settled, which will return one result for each input and not blow up. But what we can do is we can set mode to something like either, and now it'll run through all of those effects. And whenever one of them is a failure, it'll capture that error and put it in the left channel. So an either is a data type that is one of two types, a left and a right. By convention, right is success and left is an error. It's used kind of like the result type in other languages. Now, these results can be transformed into whatever is necessary in this application, and I'll leave that mapping as an exercise for you. Unsurprisingly, each of these calls can independently be extended with retries and additional handlers. Our retries from earlier can be added to each of the check effects, which get passed into effect.all. So let's add a function, we'll call it with retries, which is going to take an effect and then pipe it into a logger and into a retry with our complex retry policy from above. Now, this isn't going to automatically happen, but if we go into our urls.map and we pass the URL into with retries of check of URL, now we're going to get 4 retries or up to 10 seconds of retries with jitter and back off and all of that, and eventually get to our result where site unreachable makes it to the top. At this point, hopefully you can see the utility value of defining and combining effects to get this bigger composite result. But the original implementation at the start of the video made the choice to turn failures into falses. So far, our errors have made it all the way to the caller where the run function surfaces them in those either objects. Now, those errors are genuinely useful. They're what trigger our retries, but we can do something even better. Let's construct the checks by passing through check, and then with retries, and finally, a function that'll handle our error type. Now, whenever you see yourself wrapping and wrapping and wrapping, it's likely that you probably want to do something with a pipe. So in this case, instead of wrapping with retries around check URL, we can just pipe into with retries. And the benefit here is that we can now handle the error. So once we've exhausted our retries and we still have some site unreachable errors, let's replace this with a return of false. Now, effect.catchTag is looking for a name of a registered error that's thrown. This site unreachable error is the name from our tagged error. That's the reason it was called tagged error. And so if we see a site unreachable error, then we're going to make it into this catch function. And we know that this is a site unreachable error because we are in this catch tag. And you can add a bunch of catch tag statements or even use a combined catch tags function. But right now we only have one error type, so we're going to catch it explicitly and then just turn that into a successful Boolean false value. This modification actually changed the result type of checks. Now, checks is just an array of effects that return Booleans and have no failures and no dependencies. Compare that to when we just had the with retries and the error might still make it through. Erasing things all the way down to never is actually a core part of how effect uses the TypeScript type system, because never can represent that something is fully satisfied or fully handled. And now, run is a function that goes through a list of URLs, logs the response status, returns whether the status was okay, runs a few times on failure with a complex retry schedule, and then finally it might give up by converting errors to a false value. All of this behavior was built up incrementally, and I think it's a beautiful thing. And since we don't have errors, we can get rid of this mode either and get just an array of Booleans back, just like we would have from the original function. But what if we want to start testing this? Certainly I wouldn't want to mock global fetch, but I've seen it done many times. This is where that third component of the effect type comes in, requirements. So let's start out by defining an injectable service called a checker, which has a check function that returns our effect from before. We're going to import from the context namespace in order to define a new tag that represents our service. We'll call that tag checker. And the definition is This checker is a thing that has a function that, given a URL, returns an effect with some result or a site unreachable error. And this result is just a subset of the properties found on HTTP responses, OK and status. This will make it easier for us to create mock implementations later because we won't need to create the entirety of the response data type. Now, using dependencies in effect is actually really neat. Inside of our generator function, where we call tryPromise, we're going to say const checker equals yield star, and then the checker type. And by doing that, we will get an instance of a checker that has that check function. And then we can use it just like we did with tryPromise. So instead of this tryPromise structure, we'll do checker.check URL. And by yielding checker, our effect automatically gets checker in the dependencies portion of its type annotation. The type system knows that this check function returns an effect that won't succeed unless there's a checker available. And this would work for any service, even if the service has a dependency on another one, and so on. And this requirement persists all the way through our implementation. So checks is an array of effects that need a checker, and run is an effect that returns a Boolean, doesn't have any errors, but it won't work without a checker. And that's why if we run our program, we get a service not found checker error. This requirement made it all the way out to effect.runPromise and then failed. But TypeScript knew about this problem before we ran our program. Here we have a type mismatch. Effect.runPromise only accepts types that have never as a dependency. So if there's any outstanding dependencies, runPromise is just going to blow up, and it's going to register that in its types. So how do we pass this dependency in? Well, we're going to need an implementation of checker. Now, it's common in effect to create multiple implementations of your services, and in this case, we ended this one with live. So checker live is a service that has a check function and actually calls a real fetch. These are going to be your production-ready implementations of a service. Then down here, we can pass in effect.all, we can pipe into effect.provide. That's how you provide these implementations. Checker live. And just like that, we have the same behavior as before, but we have an injectable dependency of this checker type. And this did erase the dependency type of checker from the type of run. And technically, we could have done this earlier by passing this into our pipe function under checks. Let's do a effect.provide of checker live. Technically, this would work too. This is just an earlier composition where these checks themselves have the dependency satisfied. You can use these building blocks to construct whatever behavior or whatever dependency graph you're looking for. But in this case, I think that it's more appropriate to pass the same checker to all of our checks. Now imagine that we wanted to see how the program would react to a specific site being down. All that we would need to do is swap out the checker with one that has that desired behavior. Let's make one right now. I'm going to take our checker live, and let's call this one checker test. So if the URL includes a /2, let's fail by returning an effect.fail, and this will be a new site unreachable error. We'll pass in the URL, and the cause will just be, the string failure. But if it succeeds, then we'll just return a effect.succeed of OK true and status 200. Now I'll replace the rest of this, and now we have an implementation that will do what we need. Imagine that you could construct this inside of your test, either as like a before or something inlined, part of the way that you are constructing the situations that will give you a specific outcome. Now, if I pass this checker into our implementation and we run it, we'll see that we have that failure site unreachable error on example.com/2, but we still have all of the behavior around it that ultimately results in a Boolean true, true, false, true, true result. Now, this is a really simple mock, but we could create something a little bit more complicated with a effect itself. So in this case, we can fail the first 5 requests that ever make it out of our implementation. No matter what the URL is, if there are failures remaining, we're going to decrement that and then return a failure. Now, with this one in place, we should eventually end up succeeding. So let's provide this as our checker implementation. We'll see errors on the first 5 requests that ever occur across a bunch of different URLs, and then ultimately we end up with an entire true result in our function. Extracting behavior into injectable service layers helps keep business logic tidy and testable, while effect composability allows really complex behavior to be gradually introduced when needed. The thing about effect-oriented programs is that their functions tend to be really stable and self-contained. When stakeholders change requirements, you don't need to rework the entire system to do what they need. Which is even more important when the changes are being written with agents that struggle to get the big picture of a codebase. There's a lot more to effect, but I wanted to start by describing the core parts that I interact with every day: errors, retries, dependencies, and generator functions. Now, if you liked this, consider leaving a comment to help guide future video topics. This has been Code and Stuff. Thanks for watching.